Hello everyone. So in the last lecture we discussed about the design of axially loaded column with minimum eccentricity. Okay, so we discussed that uh, as per your clause number 39.3. okay, we check of IS 456 2000, we check the column for your minimum eccentricity by using the formula E minimum equal to L over 500 plus D over 30. Okay, it is subjected to minimum of 20 mm. Okay, so this is given in your clause number 25.4, this formula 25.4. okay, so as per this clause 39.3, okay, so a short column which is axially loaded, it should be designed for minimum eccentricity, which is given by this. Okay, so where L is the unsupported length of the column and D is the lateral dimension of the column. So if this value of minimum eccentricity calculated, it is less than or equal to 0.05 D. Okay, this is mentioned in clause number 39.3. then code permits the design of short axially loaded compression member by using the equation as PU equal to 0.4 FCK AC plus 0.67 FYAS. Okay, so but however, if the minimum eccentricity is greater than 0.05 D, okay, then the section should be designed for combined axial load and bending. Okay, so here in this video we'll discuss the design of that column where this eccentricity is exceeding 0.05. okay, so we term it as design of column with axial load and uniaxial bending. So let us assume a rectangular frame here. Okay, so I'll just give you that importance of this axial load and uniaxial bending, how why it is important to design the structure for bending also. Okay, so let us assume a rectangular frame. Okay, so if this is a rectangular frame, then we are having beams. Okay, so let us make a frame here. It is very much important to understand. So this is a frame which is rectangular in shape. Okay, so when so these are your beams which are provided here. Okay, and we need to design the column for this frame. Okay, so if we want to, this is a rectangular section. Okay, so let me just describe you first that if it is a rectangular section, okay, then the tendency of this frame to the loading will be like, if this is a rectangular building like this, so the tendency of this will be to bend like this or this more. Okay, instead of bending like this or this. Okay, so what happens, we need to design the column for this section on the basis to resist this bending. Okay, so if we are using square or circular column, so we need not to take into account the orientation of these two shapes while designing the column for the frame. Okay, but if we are designing the column as a rectangular, okay, rectangular shape, then we obviously need to check what should be the orientation of this column in the building. Okay, whether we should use the column in this manner or in this manner. Okay, so obviously to resist the loading, okay, so we need to provide the column section like this way in this frame. Okay, so we'll provide the column section here like this way. So why this is important, because we will have bending in this direction. Okay, so we need to provide the resistance, maximum resistance towards the area where the second moment of area is very less. Okay, so to resist that, so we need to provide the structure, to provide the column like this way. Okay, so now next important thing we need to take here is that, so we you can see here that these columns we are using here, if we look into the corner columns, okay, this one, this one, this one, and this one. Okay, so you can see here they are uh, imposed by your axial loading, as well as they will experience some bending here. Okay, if the length of these beams, okay, we are provided in this frame, length and loading are not changing, or they are constant, then we can say that in the corner section we will experience the axial load and bending also. Why? Because you can see here there is no excess of symmetry now, okay, for this column section. So we have the equal distance here and equal distance here. Okay, so there will be tendency of this column under this axial load to bend in two directions. Okay, in this and in this. So we have two directions here in which this beam section, this column section will bend due to this axial load when we are talking about this corner column. So it will happen in all these corner columns. Okay, so but if we take this column here, okay, so it is it will experience no bending here. Okay, so it will experience the bending will be experienced due to load in this direction only. Okay, so we can say that this column is in this column the bending is in one direction. Okay, and in this column the bending is in two directions. Okay, in x-axis as well as in y-axis. So this is called biaxial bending, and this is called uniaxial bending, because what is happening, along with the axial load the column is experiencing some bending also. Okay, but if you look at this column, so it will have just axial loading here. Okay, it will not experience any type of bending here. Okay, so we can see from here that we in this frame structure we need to design the column in three manners. Okay, first one for column with axial loads only. Okay, and for this column we need to design the column for axial load plus uniaxial bending in the one direction, and in this column we have to design the column for axial load plus biaxial bending. Okay, so in this framed structure we need to design the columns in this manner. Okay, so now here we have three cases to discuss. Okay, when your pu and mu both are acting on this frame. Okay, so what are those cases? When pu equals to 0, and second one is when mu equals to 0, and third one is when pu and mu both exist. Okay, so we need to discuss this. When pu equal to 0, it means axial loading. Okay, when your axial loading is 0 in the structure, then it means that it is a case of pure bending. Okay, only bending is acting, so that this section will behave like a your doubly reinforced beam section. So this will behave like a beam section only. Okay, so when your mu is equal to 0, okay, when there is no moment acting, okay, so then it means it is axially loaded column. Okay, So when PU and MU both exist, okay, so when it is at the third case, when PU and MU both exist, so in this case we need to find out the what is the strain that is occurring uh, at the outermost compression fiber of the column section. Okay, so for this section, let me draw here. If I draw the section like this is your B and this is your D. Okay, so for this section, if it is acted by axial loading at the center with minimum eccentricity, okay, so then the your maximum strain in the outermost compression fiber, it is given as 0.002. okay, 0.002. we have discussed in the assumptions of this your axially loaded column design. Okay, so if this section is acted by both PU and MU, okay, so in this case the strain in your outermost compression fiber, okay, it will be given by this diagram, and the strain in the outermost fiber will be 0.0035 minus epsilon of C. If this the strain in the least compressed fiber is your epsilon C. Okay, so this is the assumption we have discussed for bending, in case of bending. Okay, so this is the case where no bending is there in the column section, and this is the case where bending is occurring in the column section. Okay, so we need to study in detail that how we are going to calculate this strain and what will be the section we need to design for the column for these strain values. Okay, so now let us understand the concept in further in detail. Okay, so let us take a column here, because we are going to design here for axial load and bending. Okay, so let it is acted by your axial load as PU. Okay, and there is acting also bending here. Okay, so the moment is acting in this direction. Okay, so let it be M. Okay, so let us take this section here. So we'll draw the section here, okay, for this column. So this is the section, so let it be B and this value be D. Okay, this is for the column. So first thing we need to understand here, what the thing is that we need used to say mx and my. Okay, so moment in x or moment in y. So what it exactly means. Okay, so if this is a section, and then these are your two direction, that is x and this is y and this is x direction. Okay, so then mx, what mx means, that this moment is acting along x direction. Okay, in along x. Okay, and it is acting about y axis. Okay, this is what it designates. And if we are talking about my, okay, then this moment is acting along y axis and it is acting about x axis. Okay, so this should be very much clear while understanding the topic furthermore. Okay, so here what we are describing, okay, so we are describing here that this loading is acting here, and due to this loading there is a bending acting along x direction, okay, about y axis. So we will designate it as mx. Okay, here, so let the moment is acting here as mx. Okay, so what is our main objective here? So we want to resist this PU and MU. Okay, we want to design this section so that it can resist this both these two things, that is PU, that is the axial load, and the moment that is acting due to this axial load in the column. Okay, so what we can do, we can increase the depth of this section. Okay, so if it is just acted upon by pu, then we can use the section, a square section here. Okay, we can easily use the square section. But if it is it is being acted by moment along with this load, axial load, then we need to provide extra resistance to that moment in the column. Okay, so for that, what we need to do, so here what we can do, we can increase the depth of the section. Okay, so when we increase when we increase the depth of the section, it becomes a rectangular section. Okay, so in that case, we need to provide, when there is your axial load and bending, so it is obviously safe to provide your beam section as rectangular, column section as rectangular section. Okay, so now if we are providing the section, a rectangular section like this, and this is B and this is D. Okay, so then what we are going to do here, we are going to provide the reinforcement in the section in this manner. Okay, in this manner. So we'll provide the reinforcement in these two rows here. Okay, why we are going to do this, why we are not distributing this like we do in the square column or axially loaded column like this. Okay, why? Because we need to take the maximum benefit of this reinforcement here. Okay, and that we can take when we will provide these reinforcement at maximum distance from the axis of bending. Okay, to resist this moment. Okay, this is in the case of uniaxial bending only. Okay, but if it is a case of biaxial bending, then we can provide the your reinforcement like in this manner. Okay, so if your bending is in both direction, x as well as in y direction, but here we are discussing the case of your uniaxial bending. Okay, so for axial load distribution, we can just provide the reinforcement like in this manner, or but if we want to provide the reinforcement for axial load plus moment, then by uniaxial bending, then we can provide the reinforcement in this manner. So I hope you understood this now. So now let us discuss the Codal provision for your axial load and uniaxial bending. So let us consider a beam section here like this, a column section, cross section here, that is that is width is your B and depth is D. We are taking here rectangular section because we have already understood that it is more convenient to provide a rectangular section for uniaxial bending case and axial load. Okay, so let us take the stress strain distribution first for this. So we have the stress strain distribution for concrete like this. So it is your 0.0035 maximum strain, and here somewhere is your 0.002, and the maximum stress in the outermost compression fiber is 0.446 FCK. Okay, so this is the stress and strain distribution. So if we just plot this strain diagram for this section here, so let us take it. So this is the line. So here somewhere at this point, about 3/7 D from here, and this value is 4/7 of D. Okay, so here is the value. So we get the maximum compression as a maximum strain in the highly compressed zone. This is your highly compressed fiber. Okay, at this time. Okay, so this is the highly compressed fiber. So if this is your strain, then this value, its value is 0.0035. okay, so here is the value which is 0.002 strain. Okay, so now we'll join this. Okay, so this is the strain value, okay, when your neutral axis is at at this, that is least compressed side of the column. Okay, so this is the maximum strain in the concrete column at the highest highly compressed fiber. Okay, so now what we take it as a pivot point. Okay, and we assume that this section, okay, this section is pivoted at this point, so this is going to rotate like this or this. Okay, so if we consider, it is going to rotate like this or this. Okay, but what is happening, because the maximum allowable strain in the concrete section is 0.0035, we can't go beyond this strain in the concrete. So what is the case, that there is another case that we study, that it get rotated about this point like this. Okay, so this is the next value we are getting. So here we are getting some strain value, and this strain value is equal to 0.0035 minus 0.75 of epsilon c, and if this value is your epsilon c, the strain value here. Okay, so what is the point to be noted here, that so when your neutral axis is at the edge, okay, then we are getting the strain diagram like this. Okay, so when your neutral axis, now you can see for this, when it is starting to rotate about this, we are assuming that the column section is so this strain diagram, so this line is pivoted to this point. Okay, this point, and it is starting to rotate. So when the bending acts, okay, in the column, then this neutral axis start to shift from here to here. Okay, so here in this case you can see the neutral axis has shifted toward this side. Okay, so now we can see here this neutral axis is being shifted here, and there is a change in strain in the outermost compression fiber. So we need to calculate that outermost compression fiber strain. So here also if we draw the stress curve for this strain, so we can get here the value as this. Okay, so this will be the value. So we can see here the for this value, this strain we are getting, okay, for the section. So but when this neutral axis shift to outside, then the diagram the stress diagram will be like this. Okay, so when you can see here that in this we need to calculate, you can see here we need to calculate the area of this curve. Okay, area under this curve. Okay, so because the column section is here, so here your effective stress taking area of the column is this only, this part. Okay, and this part is not taking any stress area. So you can see when this neutral axis is shifting outside the column section, then we can this area is increasing. Okay, this is increasing, so we are interested in calculating this area. Okay, and you can see when this neutral axis will go to infinity. Okay, when this neutral axis reaches infinity, then this strain line will move like this. Okay, so if this is, so it is moving here. Okay, we are getting this curve and the stress curve, and after that it will move like this, and then finally it will reach at infinity. So when it will reach at infinity, then the strain in the whole section will become 0.02. Okay, so that's why we take for this is the case when your axial loading acts on the column section. Okay, we have discussed it. So we have discussed all these things in assumptions part. Okay, so here we are interested in calculating this area. Okay, so now what is the main objective? Main objective is to know what is the value of P and M. Okay, so what is the value of P and M for this section to behave safely. Okay, so we check it for different values of neutral axis. Okay, so we check the value of this P and M for different values of neutral axis for this column section. Okay, so what is the moment of resistance and resistance for the axial load that we calculate for a particular neutral axis position here in nutshell. Okay, so then we plot a graph for this P and M. Okay, so that graph is called your curve interaction curve. Okay, or we can say that column interaction curve, because this is a very iterative procedure, because now you can understand that we need to calculate the maximum strain at this outermost compression fiber. So we need to do it by trial and error again and again. Okay, so the method is very lengthy. So what Indian standard 456 recommend that we should use a special provision that is given as SP16 for IS 456 2000 for this interaction curve. Okay, so instead of just doing or calculating this strains in the outermost compression fiber for different value of these neutral axis. Okay, so what we do, we prepare a curve here. Okay, so SP16 is that is special provision for IS 456 2000 for the design of columns. Okay, so we have a column interaction diagram. So what is in the column interaction diagram? Okay, we draw the curve for different area of steel, for different grade of steel, and for different concrete. We draw a curve between your PU, P and M here. Okay, so what we do, we would like to draw a curve. Okay, so the curve is like this. Okay, so this curve is plotted by first area of steel, okay, that we are going to calculate for the particular section, and second one is the grade of steel that we are going to use, and third one is the concrete. Okay, concrete, that is FCK, that we are going to use here. Okay, so it means that let us take a section and find out how much load and how much moment it can take for a particular neutral axis position. So that's why we draw this diagram. Okay, so here you can see we can plot the diagram for area of steel. So we have different area of steel. What we can do, what we'll do, we will take a particular section, okay, first, and then for this particular section we will calculate how much load and how much your moment it can take. Okay, so this section, how much load and how much moment it can take for a particular area of steel. Okay, so and for particular position of your neutral axis. Okay, so what we do, we'll draw this curve for area of steel first. Okay, so for particular percentage of steel we'll draw the curve, then for another percentage of steel we'll draw another curve here. Okay, and for change another percentage of steel we'll draw another curve. Okay, so in the same manner we draw the curve for different grades of steel, like for 415 we will draw like this, and then for 500 we'll draw like that. Okay, so these all curves which are drawn between P and M, these are given in your SP16. Okay, so now one more important thing here, what we take here, we take PU over FCK BD here and MU over FCK BD square. Okay, and the percentage that we get here, percentage of steel that we get here, it is given by percentage over FCK. So this diagram is represented in the in your SP16 like this only. Okay, so here we are using pu over fck bd and mu over fck bt square. So there is no any linear relationship between pu and mu. Okay, so what we do, we calculate these two values, we divide it. What is fck? Fck is the grade of the concrete, okay, the characteristic strength of the concrete. And what is b and d? B and d are the your these dimensions of the column. Okay, so we calculated. Why we are doing this, it make this value, these two values, okay, dimensionless. So we are using they like this, these values, for the proper better interaction, okay, between the two. So what is the main thing here? So what we do for a particular section, okay, for a particular section of column, we calculate the percentage of steel for the load and the moment that it is going to take. Okay, so this is the column interaction diagram. So we are going to use this column interaction diagram in your calculation of steel for the column when we are going to design it for axial load and uniaxial bending. So this is the important thing here. Okay, so we'll take a numerical problem on this, so to understand this. And one another thing here I would like to say that this column interaction diagram, it has three points here, okay, different points here. So this is your we are drawing this curve for different positions of neutral axis, okay, as I have discussed. So this says we are starting from here, that is 0.002, okay, and we are moving toward 0.0035. This is the maximum strain. So this is the position when there is maximum strain. Okay, so after that, if this neutral axis comes within the section, okay, it comes within the section, then there is a case of pure bending. Okay, there is no axial loading, then it is a case of pure bending. So we have three parts here. So this one is your axial loading, okay, and somewhere here we have a balanced section, and here we have no loading, no axial loading, okay, axial loading. And this point, okay, this point is called the your pure bending zone, okay, pure bending. And this is the here, and there is no any movement. Okay, so now this part is called your tension zone, okay, and this is your compression zone. So particularly these are the parts of this interaction curve. And what is the most important thing here? The most important thing is there that we are going to use this interaction diagram for the calculation of area of steel for the given problem, for the given section. Okay, so we'll see while solving the numerical problem that how these diagrams can be used to calculate the steel here. Okay, and one more thing here is that this interaction diagram can be used. We are using this interaction diagram because we can't because the method, the iterative method, that is it in trial, we can say trial and error method, that is very much laborious to opt, okay, to calculate the values. Clear? So this is all about the design of column with the axial load and uniaxial bending. Okay, in the next video, we'll discuss a numerical problem based on the design, and also we'll see how to use the interaction curve to calculate the steel for the given section. Okay, so thank you so much.